Hello and welcome to today's class. So, as a continuation from where we had left off in last class, we will start discussing about confidence intervals. Okay. So, just to remind you of what was covered in last class, okay, we had shown that given that we know that 95% of the data lies between plus minus 2 standard deviations, and given that for a sample mean, for example, you know that x bar minus mu by sigma by root n is the confidence interval, okay, is the standard normal variable. So, you know that this probability is equal to 0.95. So, using some basic algebra, you can show that mu lies between x bar minus 1.96 sigma by root n and x bar plus 1.96 sigma by root n. Okay. This probability is 95. Okay. So, in other words, the 95% confidence interval lies between x bar minus 1.96 sigma by root n and x bar plus 1.96 sigma by root n. Okay. So, this is your 95% confidence interval. In other words, so as we had shown and discussed in last class, if this is your true population mean, then if you do this sampling, then bulk of the times you will have your population mean lie between your range. This pen also does not work, that is right. Okay. So, 95% of times, okay, this interval will contain your mean. Okay. That is what the 95% confidence intervals mean. So, if you have seen experimental data being represented, okay, experimental data being represented, very often you will see data being plotted as you have a bar and you have something which is sticking out on both sides. Okay. So, let us say hypothetically it is height of population of the class or so on and so forth. So, what does this mean? When data is plotted like this is your average or mean, okay, or mean value, okay, and this is called the error bar. Okay. Now, this error bar can be either your standard deviation or, okay, or instead of standard deviation you can plot sigma by root n. Okay. This is also called the standard error of the mean. Or in short it is referred to as SEM. Okay. So, in papers or in research articles you will see data presented as mean plus minus SEM. Okay. So, this is called the standard error of the mean. Okay. So, if your sample size is small, then your standard deviation is going to be significantly higher. Okay. So, in that way, instead of plotting the standard deviation, okay, so for the same data, let us say for the same data, if this is your mean, let us say this is your standard deviation. Okay. This representation does not look nice, but if you plot the same data with the standard, so this is with standard deviation, okay, and this same data is plotted with standard error of the mean, and you will see this is significantly high. And what is the reason for that? Because the standard error of the mean is sigma by root n. Okay. Even if you have n is equal to 4, then this is going to be half its size, okay, sigma by root 4. So, this is going to be half its size. So, that is why if you have, if n is reasonably large, then standard deviation is also not so spread out, okay, it is less, but standard error of the mean is even lesser. So, it is sometimes it is helpful to present your data as mean plus minus SEM. Okay. So, instead of having an interval estimate which gives the both the minimum and the maximum, you might have. So, the 95% confidence interval, okay, okay, gives us x bar plus minus 1.96 AC or 1.96. So, this is AC is sigma by root n. Okay. So, let us take an example. Okay. Imagine the signal having value mu is transmitted from A to B, okay, and the value received at B is normal, is normally distributed, with mean, okay, with mean of mu, okay, and variance, okay, of 4. Okay. So, to reduce the error, okay, the same signal is sent or transmitted, okay, 9 times, okay, and let us say, okay, so the 9 times you have sent it, and what the signals that the value is received are as follows. Okay, it is 5, 8.5, 12, 15, okay, 7, 9, 7.5, 6.5 and 10.5. Okay. We want to find out the 95% confidence interval. Okay. So, what do we have? We have, so 95 confidence interval. So, your average, okay, your average is mu. Okay. So, the average of this, okay, average of this is 5 plus 8.5 plus 12 plus 15 plus 7 plus 9 plus 7.5 plus 6.5 plus 10.5 by 4, 5, 6, 7 by 9, and this should come out to be, so if you plug in the values, this should come out to be 9. Okay. So, this would mean, okay, this would mean my 95% confidence interval has to be 9 plus minus, okay, 1.96 into sigma by, okay, root of 9. Okay. So, if you plug in the values, this comes out to be 7.69 to 10.31. Okay. So, this tells us that we are 95% confident that the true message lies between 7.69 and 10.31. Okay. Okay. So, instead of having, okay, a lower and an upper limit, you might also be interested in finding out a lower limit. Okay. So, we can have what is called a one-sided interval estimation. Okay. So, for doing that, for standard normal variable, we know that z less than 1. So, 1.645 is equal to 0.95. Okay. So, we can put x bar minus mu by sigma by root n less than 1.645 equal to 0.95, and this would give us probability of mu greater than x bar minus 1.645 sigma by root n equal to 0.95. Okay. So, again the 95% confidence interval. Okay. So, this is the one sided upper confidence interval for mu will be given by x bar minus 1.645 sigma by root n, okay, comma infinity, because this is the lowest value of possible for mu. Similarly, you can calculate an absolute upper value. Okay. So, the one sided lower confidence interval, okay, for mu turns out to be between minus infinity to x bar plus. Okay. So, this is what you have the confidence intervals created for one sided. Okay. So, this set stipulates the lower bound for, so this stipulates the lower bound for x bar, and this stipulates x bar 1 plus 61.5 sigma by root n stipulates the upper bound for x bar or mu. Okay, sorry, mu. Okay. Now, these cases, okay, for all these cases we have assumed the 95% confidence interval, right. Okay. But theoretically we can calculate the confidence 50% confidence interval or 90% confidence interval and so on and so forth. And statistically what people typically use may be the 90%, the 95%, the 98% or the 99% confidence intervals. Okay. So, how do we calculate the 90% and all these other confidence intervals? So, what you need to note, okay, okay, okay. So, let us say we have this interval, so this is 0. Okay. You have this normal distribution is symmetric. Okay, this value is minus z alpha by 2 and this is z alpha by 2. So, this corresponds to that the area under this curve is alpha by 2, the area under this curve is alpha by 2. So, what is in the center? This is going to be 1 minus alpha. Okay. So, we can calculate, okay, okay. So, we can find out probability of minus z alpha by 2 less than z alpha by 2 equal to 1 minus alpha. Okay. And from this equation we can again write x bar minus z alpha by 2 into sigma by root n less than mu less than x bar plus z of alpha by 2 into sigma by root n is equal to 1 minus alpha. Okay. So, for alpha, so for 100 into minus 1 minus alpha is the confidence interval. Okay. So, if I plot the values of alpha, okay, 100 into 1 minus alpha, okay, in percentage you can have 95%, you can have 90%, okay, you can have 95% or you can have 99%, okay, 98% or 99%. So, the corresponding values of z alpha by 2 for 90% it is 1.645, okay, for 98% it is 2.33 and for 99% it is 2.58. Okay. So, this would mean so if you want to calculate the 99% confidence interval, then we have the bound, the upper and lower bound becomes x bar plus minus 2.58 sigma by root n. Okay. So, this is the 99% confidence interval for mu. Okay. So, let us take a sample example. Okay. So, let us say a dietitian selects a random sample of n equal to 49 adults. Okay. Of, so what the dietitian is probing is the daily dairy product intake. Okay. And what it finds is, on an average, x bar is equal to 750 with a standard deviation s equal to 28. Okay. So, we want to calculate the 90% and the 99% confidence intervals. Okay. So, as per this calculation, for 90%, so the confidence interval for 90% confidence interval will be, okay, your x bar, okay, plus minus 1.645 into s, which is 28, and n is 49. So, root of 49. So, it is x bar plus minus 1.645. So, this is into 4, okay, and the 99% confidence interval will be x bar plus minus 2.58 into 4. Okay. So, what you can clearly see is this magnitude is, so this is a tighter limit. In other words, if this is the interval length for 90%, okay, the interval length for 99% is larger. Okay. The interval length is larger. So, this increases the chance that the population mean will lie within it, versus if you choose a tighter range, it is likely, it is possible, there is a greater chance that your population will be lie outside this. Okay. Okay. So, okay. So, these were the population means. So, once again I would like to reiterate, okay, that for greater confidence interval range, okay, we always have a bigger interval, and for smaller range, so for 90% you have a smaller interval. Okay. So, there is a greater chance of error that your population mean will not lie within this limit. Okay. So, that also brings us to another point. Okay. So, let us say if I want, so your confidence interval length, so your total confidence interval length is what? It is basically x bar plus, let us say if you want a 95% confidence interval length, okay, 1.96 sigma by root n minus x bar minus 1.96 into sigma by root n. Okay. This is 2 into 1.96 into sigma by root n. So, this is your confidence interval length. Okay. So, accordingly, for 99% confidence interval length, this will be 2 into 2.58 into sigma by root n. Okay. Let us consider a simple example, okay, and the question is as follows. Okay. How large a sample is required to ensure 99% confidence interval length equal to 0.1. Okay. So, what we have to do is we have to set 0.1 is equal to 2 into 2.58 into sigma by root n. Okay. So, based on this you have an equation where you have root n in this equation. Okay. So, we can from this equation, so we have 2 into 2.58 into sigma by root n, okay, is equal to 0.1. So, from this, okay, I can calculate n is equal to 5.16 into sigma whole square. Okay. So, what you see, your n has a sigma square dependence. Okay. So, if you want the 99% confidence interval to be a certain range, then your n has to be much larger. Okay. So, till now we have discussed, about calculating the confidence intervals for one particular value, but in experimental cases, in the general case, what we are often interested is to compare the effect of two different situations to probe the effect of a particular molecule or some particular measurable metric. In other words, let us say you have a patient, okay, and the doctor wants to understand, okay, the doctor is considering of administering drug A or drug B, okay, and he wants to understand which of these two drugs will be much more effective for a given population. Okay. So, the question is which drug is more effective. Okay. So, how do we address this question? Okay. So, this brings us to the concept. Okay. So, imagine you had this drug A, you administered it with n1 number of n1 sample in the population, okay, and from this you have measured the response in terms of a mean response, okay, mu 1 and a mean variance sigma 1 square. Okay. So, if it was for the whole population, this is sigma 1 square, but if it is for a sample, it is S 1 square. Okay. Similarly, for drug B, you had N2, you sampled N2, okay, and the population means can be either mu 2 and sigma 2 square or S 2 square if it is for sample, this is for a population. So, this brings us to the question of estimating, okay, difference between two population means. Okay. So, what we want to know, okay, that so if you have two random variables x1 and x2, okay, this is corresponding to the drug response of A, this is corresponding to the drug response of B. Okay. So, we want to calculate x1 bar minus x2 bar, and this you would intuitively think that this is the best, okay, point estimate, okay, of mu 1 minus mu 2. Okay. And I can say that this random variable x1 minus x2, okay, this would follow a normal distribution, okay, with mean mu 1 minus mu 2, and what is the standard deviation? Okay. And the standard deviation, which has to be sigma 1 square by n plus n 1 plus sigma 2 square by n 2. Okay, standard deviation, this is a variance. So, this is the standard deviation. Okay. So, the standard deviation will be this one. Let us take a simple case. Okay. Once again, so your x1 bar minus x2 bar will have a mean of mu1 minus mu2 and variance, okay, which is going to be sigma square by n1 plus sigma 2 square by n2. Okay. For example, take a simple case. Okay. Let us say you are comparing the you are comparing the performance of two tires. Two tires, okay, from two companies. Okay. And you have been given x1 bar as 26,400, x2 bar, okay, and both n1, okay, so x2 bar as 25,100 and n1 equal to n2 equal to 30, okay, s1 square as 1,440,000 and s2 square as 1,960,000. Okay. So, what you will do? You will calculate mu1 minus mu2. Point estimate of mu1 minus mu2 is x1 bar minus x2 bar, and this is 1300. Okay. And you can also calculate. So, for this you can calculate this quantity, square root of this as the standard deviation, and you can calculate the 99% confidence interval. Okay, which is given by x1 bar minus x2 bar plus minus 2.58 times root of s1 square by n1 plus s2 square by n2. Okay. And if you plug in the values and you see this is always positive, then this would mean that this the tire from company 1 is going to be better than tire from company 2. Okay. If so, let us say, so I do not know the exact value for this. Okay. Let us say it comes out to be between 800 and 1800. Okay. So, let us, if this was the range, then you know this is always positive. So, you can comment that with 95% confidence you can state that tire A is better than tire 2. Okay. So, this is how you can make use of confidence intervals to either get an estimate of the population mean or even compare different populations to say which is better or which is worse. Okay. With that, I thank you for your attention and I look forward to next day's class.